Okay, let's get started. Just a reminder for the next 75 minutes, this is a device-free zone with the exception of this particular device here. Let's talk a little bit about the deliverables. So deliverable 8 is due tomorrow night. And then deliverable 9, you can start in on Thursday. However, I'm going to be traveling on Thursday, so I put up deliverable 9 a little bit early if you want to get started on it. And we'll talk about deliverable 9 in a moment. I apologize that I'm doing so much traveling this semester. This is not normal for me. I will be in Chicago on Thursday for a DARPA meeting. DARPA runs a program called Lifelong Learning Machines. So at the moment when we train AI and deploy it out into the world, it's done learning and it does whatever it does. There are situations where it makes sense that once you deploy an autonomous machine out into the world, it continues to learn. It's a challenging and risky thing to do. So there's an interesting meeting about that. I will be there. In my place, Professor Bagro from the math department will be here. Some of you may have been taking or are taking Professor Bagro's data science class. Professor Bagro does research in data science, but also in crowdsourcing, which we talked about a few weeks back. So he will be here and talking about some of his crowdsourcing research on Thursday. As I mentioned, whenever I travel, I bring back food to bribe all of you. What should I bring back from Chicago? Pizza. I knew I was going to get that one. No deep dish pizza. I would if I could. I will find something and bribe you the following Tuesday when we move on to lecture, probably lecture 17 or 18. We'll see where we are. Okay, so I won't be here on Thursday, but we'll continue on with the deliverables as usual. So let's spend a few minutes just talking about the deliverables now. I just want to back up for a moment to deliverable 6. I realized now that there was some confusion in deliverable 6 at step number 7. And the reason why is some of you may have got an error at this point where your KNN algorithm does not accept test data. Why not? Turns out it depends on the version of NumPy, which was part of the problem. It worked for me, but not for everyone else. What is the shape of the test data structure?
Because it's sometimes, depending on the version of NumPy, it might return two-dimensional, where one of the dimensions is just one.
Exactly. So technically, what we're defining here is a two-dimensional matrix that has 1 row and 30 columns. What we really need is just a vector with 30 elements, right? But of course, a 1 by 30 matrix is equivalent to a vector, according to some versions of Python and some not. So if some of you are still struggling with deliverable 6, the easy fix is to go back and just define np.zeros, open bracket, 30, comma, dtype, and so on. So just a vector of length 30. If you put in brackets a series of numbers, you're defining an n-dimensional matrix with rows, columns, sheets, and so forth. If you just put a number in there, you're telling it you want back a vector of length whatever. Okay, I think most of you are past this. However, hopefully you're finishing up deliverable 8, and deliverable 9 is now available. Last time, this was perfect timing, we ended last time by talking about this concept of scaffolding. Scaffolding is an idea that comes from developmental psychology about how parents scaffold the learning experience of children. We saw the little picture last time of the parent walking the child through the process of walking, so the child can literally feel what it feels like to walk. So the parent is scaffolding the experience of the child, making it easier for the learner to capture to start the rudiments of, to master the rudiments of the task. And then as the teacher or the parent or the instructor starts to observe that the learner is getting the idea of it, as the name implies, the scaffolding is gradually removed. What are some other examples of scaffolding?
Actual scaffolding as the building is being created.
Makes it easier to build the building, right? That's what the scaffolding is there for. Yes, literal scaffolding. Where else?
And like how to draw X books, where they like start out in a circle and then you build on that.
I'm sorry, what is this?
Like how to draw like X books, like how to draw animals or whatever.
Oh, okay, where you actually
Yeah.
trace over the drawing?
No,
Oh.
where it's like they say like draw a circle.
Okay.
And then they say now add the line to that circle. And then they say now add these.
Yes, exactly. So step-by-step drawing instructions.
When you first play the game, like there are all these instructions that tells you how to move the character, how to jump, how to do whatever. And then as you go on, those instructions.
Absolutely, right? So in-game tutorials, which is exactly what you're going to be building in Deliverable 9. How did you learn to ride a bicycle? Some of us. Your training wheels, right? Another good example of scaffolding. Remove the training wheels. This idea of scaffolding is also prevalent in AI. So as an AI is starting to learn a task, you might make the task easier on the AI, and as it starts to get the idea, gradually remove the scaffolding. Okay, so in Deliverable 9 and 10 now, you're really starting to develop your educational software. So in Deliverable 9, you're going to be adding 3 pieces of scaffolding. Let me just back up here. In the first case, you're going to challenge the user to sign an increasing number of digits. So the first time a new user logs in to your system, you may pick one of the 10 digits, show them the image of the sign for that digit, and wait until they sign that digit correctly, and then show them a second digit. They sign that correctly, go back to the first digit, and you might alternate back and forth between just 2 digits until they master those. Once they master those, you expose them to a third digit, jump back and forth between those 3 digits. Once they master those 3, 4, 5, 6, and so on, right? You can scaffold the learning of all 10 by exposing them to a small subset of what they're supposed to learn, and as they signal increasing competence, broaden the things that you're trying to teach them. That's the first scaffold. The second scaffold will gradually challenge them to remember the sign itself. We talked a fair bit in this course about recognition versus recall. So eventually they need to just recognize the picture and figure out how to do it themselves, but eventually you're going to just draw the digit 0, 1, 2, and so on, and they should remember what the sign is and do it correctly. We could go from just showing them the image and then at a certain point not showing them the image anymore, but we'd like to do this using scaffolding where we gradually challenge them to remember the sign, and there are different ways you can do that, and it's up to you about how to do that. So in assignment 9, in Deliverable 9, you're creating 3 forms of scaffolding. The actual way that you do it is up to you. Okay. And then the third scaffolding is to increasingly challenge them to sign that gesture faster and faster. So put increasing time pressure on them from the time of signaling which particular digit they're supposed to sign until correct signing of that digit. We want to try and reduce that time. Okay, so pretty short in terms of the instructions, just 1, 2, 3, these 3 scaffolds, and then we want you to upload 3 videos showing those scaffolds in action. So in each of the 3 videos, you're going to intentionally make mistakes, and the scaffold will remain. And then as you get better in your video, we should be able to see the scaffolding being removed. And again, remember, we're assuming our user is not a native English speaker here, so no text. It should be obvious from the visuals that the scaffolding is being removed. Make sense? Okay, so back to lecture material for those of you that are just joining us. I won't be here on Thursday. There'll be a guest lecturer, but Deliverable 9 is available now if you want to start in on it. Okay, so we're going to finish lecture 16 in a moment, which is this idea of ubiquitous computing, or sort of stitching devices out there into the real world. And as we do, there are more and more of them. They're specialized, they only do a few things, and as we stitch these specialized devices out into the world around us, they kind of disappear into the background, and they are there to support us and possibly scaffold us as we go about our daily business and help us out in various unobtrusive ways. It's interesting to think about as we do that, sort of what are the killer apps? What are the things that we can, what are the things that we can enable people to do that would have been difficult or impossible to do in a physical world in which there is no embedded technology? And to explore that question, in lectures 17, 18, and 19, we're going to look at 3 different projects. They're research projects that ask the question, once you have the technology out there, what are some things that you can do that are difficult to do otherwise? The one that we're going to look at today is the idea of social network inference. You're all aware of what social networking is. On Twitter or Facebook, you can see what the social network is. I'm on Facebook. I have all of my friends. I see about 30 of you out here, but I don't know which of you are friends with who else. Is there a way that we could infer that just as you go about your everyday lives? Now, whether we would want to do that or not is another issue. But could you actually infer from just people's daily activities, could you infer a social network? Who knows whom, who spends more time with whom, who enters into more conversations with whom, and so on. And at the end of lecture 17, you're going to see that, of course, you can do that. And you can also then ask questions about social networks that are difficult or impossible to answer on social network apps. Like, for example, how do people change their social behavior depending on who they're interacting with? Do they interact differently when they're interacting with friends, with someone they know from class but don't know very well, or complete strangers? Difficult to do on social networking, but it turns out in this application you can see kind of interesting. There are interesting social dynamics that go on in social groups that were difficult or impossible for social anthropologists to see without technology. Interesting project. In lecture 18, next week, we'll look at activity tagging. So you all carry around a smartphone. Most smartphones come with an accelerometer. If you record that accelerometer data, you can actually infer, in a lot of cases, what activity the person is conducting at that point in time. Again, whether you would want to do that or not is a separate question. We're going to look in lecture 18 at just the question of how to do it and what kinds of activities can be inferred. Lecture 19, we're going to look at a speech project where an investigator and his wife instrumented their home and recorded all the video and audio in their house during the first 6 months of their child's lifetime, and asked the question about how does a child go about acquiring language? When a child utters the word water or mother for the first time, how did the child go about acquiring or learning that word? What were all the things that were going on in the house at that moment that the child uttered the word, the minute before the child uttered that word, the day before, the week before, the month before? Kind of a controversial project. This is the great, what do they call it? The biggest family home album of all time, but pretty intrusive at the same time. Okay, interesting to think about. So 3 different applications, once we have ubiquitous computing, are things that were difficult or impossible to do beforehand. So let's jump back to lecture 16, where we're talking about ubiquitous computing. We were thinking about this idea of, again, is putting technology out there in the world, and hopefully it fades into the background and it's not obtrusive, and it just sort of helps us get going with whatever it is that we want to do. That good scaffolding or ubiquitous technology in particular provides a learning gradient, a path or a slope that we can climb. So as the agent starts to learn what they want to do, literally or figuratively to stand on their own 2 feet, we gradually remove this scaffolding. We just talked a little bit about it. Okay, what are some examples of ubiquitous technology that's already out there that provides scaffolding?
How about Google Maps?
Google Maps, okay,
You
right?
directions and you follow it by yourself once you've done it.
Absolutely, right? So it doesn't explicitly remove scaffolding, but you're going to a new destination, use Google Maps a few times, and then you don't need it anymore. Good example. Okay. Let's look at another application. Before we do, let's look at some data here. These are population pyramids, which are a nice way to summarize data. Remember our discussion about visual design. These population pyramids are showing the distribution of ages in the population of a particular country in 1950 2005, and 2050. Let me zoom in a little bit here for you if I can. What can you tell me about this country? How is the distribution of age in the population changing over time?
The average age is moving up.
Absolutely, right? So people are living longer and having less children. In the Western world, you can probably guess that this is a Western country. What else is changing between 1950 through 2005 and projected into 2050?
People are living older and older ages.
Absolutely. What else?
It's weighted towards the female gender.
Absolutely. So males and females are living longer, but females are living longer at at a greater rate. What else?
Not looking too good for 2050 in terms of the total population.
Not looking good for the total population. Not looking good in what sense?
In that the total population is smaller.
Possibly. There's something else that's worrying about this projection for 2050.
In 2005 with the Z generation, like, I guess occurs that where there's a larger generation and there's some points where there's less.
Absolutely. There's a bump in the middle. There's a boom here. What boom is it? It's the baby boomers, right? So there's the baby boomers moving through the population pyramid. Why is the projection for 2050 worrying?
For political reason, but 35.7% of the population would be pretty old.
What are these three classes here, these three divisions?
By generation.
By generation, could we be a little more specific?
The light blue is below working age, dark blue is working age, and the white is above working age.
Absolutely, right?
Large
So
percentage in the non-working age.
So in this country, by 2050, there will almost be more people not working than working. Which country is this?
United States.
Not quite.
Japan.
Not quite. There's a few hints that I left up here, if you're paying attention.
The UK,
It's the UK. How did you know it was the UK?
Ministry of Health, Labor and Welfare.
There you go, the Ministry of Health, Labor, and Welfare. So this is the projection for the United Kingdom. Somebody mentioned Japan. Japan already has more non-workers than workers. They've already passed this worrying threshold. So what do we do about this situation? The US is somewhere between the UK and Japan, not as bad as Japan yet, but also headed in the same direction. So how do we go about supporting a greater fraction of the population that is not gainfully employed? There's a lot of solutions out there. Nobody really knows. One way to do that is to try and help the elderly stay within their homes and independent as long as possible. Unlike the younger generation, who are primarily taken care of by their parents, elderly populations primarily are taken care of by the state, which requires taxes, which requires people to be working in order to pay taxes, right? Becomes a challenge. So there's a big challenge facing most Western countries, which is how do we take care of our aging population? And whatever those solutions are going to be, a big part of that solution is going to be keep them in their homes and keep them independent as long as possible. That's the best solution for them, best solution for their parents, best solution for the state. How do we keep the elderly generation in their homes? This is an idea that's been around in HCI for a long time, which is the smart home, that we instrument homes with technologies that, again, make things easier for the homeowner, which in this case is someone who may have physical limitations. So I plotted a little cartoon here of one way we might go about stitching technology into the home of an elderly person. This is clearly an HCI enterprise because we need to think very carefully about the P. Who is it that we're trying to support? Physical context matters. What does it mean to be physically limited and trying to move about in your own home? What are the other social and cultural contexts that matters as you think about trying to create a smart home for the elderly? We would like to not create a Big Brother home where it's constant surveillance all the time. How could we balance surveillance with support and scaffolding? I don't know if any of you have had this experience, but with my elderly parents, sometimes I call and nobody answers the phone, and I'm not sure why. Right? So one of the things we might be able to do is to try and provide some scaffolding, provide some signaling about what's going on in the home. Imagine that we were to embed some pressure sensors into carpets throughout the home. As long as Ms. X is moving across the carpets whenever the telephone rings, there may be an automated message that's sent to the caller saying, Ms. X is approaching the phone, hold on, she's coming, for example. Okay, or not, or the phone is ringing, there are no signals coming back from the pressure sensors, and the signal is Miss X cannot hear you, or there doesn't seem to be any movement in the home. Send a message to her vibrating pager or provide some other options. I've sketched this out using what's known as the ERMIA notation. For those of you that go and work in industry and HCI, this is still often used to sketch out HCI designs. Entity relationship modeling for information artifacts. HCI loves their big complicated acronyms. Basically, it's a fancy way of showing a collection of physical objects like carpets and information artifacts like sensors or cameras or Wi-Fi devices, and showing sort of how we're going to thread these things together. What is some other technology you might think about instrumenting in a smart home for the elderly to help them maintain their independence? Yes?
Something that maybe monitors what's in their fridge, because I know as they get older, they don't want to drive as much.
Yep.
So there's some way that they could just order groceries automatically.
Absolutely. So we could set up ordering groceries automatically. We could have a camera inside the refrigerator. I'm sorry? Reminders to take their pills. I have a family member that will go unnamed. We remind this person all the time and they refuse or forget or they're not sure. It's a challenging one. Be great to actually instrument their medication box to actually be able to detect whether a pill has been removed once per day. Reminders are sometimes not enough. What else? What are some of the other challenges here? Remember pact analysis. So medication, absolutely. Food, movement matters.
You have to get more specific than just she's walking on the carpet while the telephone's ringing.
Absolutely. What else might be useful here? Assuming we have these pressure sensors in the carpets.
Say they fall.
Falls matter, right? So again, I have a family member who is supposed to wear something that detects falls, and sometimes he remembers to wear it, and sometimes he does not. Other examples?
There has to be some way that they can signal that they're in trouble, and it has to be with some non-local way, maybe.
Absolutely, right? So if something goes wrong, how do they easily signal? It better not be something that has a lot of buttons or something they need to wear because they may or may not remember, they may or may not know which button to press.
Well, I feel like Alexa actually would be really good in a lot of these scenarios because you don't have to know how to press all those buttons or you can just say like, where are my phones?
Absolutely, yeah. So voice-activated technology is clearly going to be an important part of whatever the solution is. Yeah, exactly. Okay, so something interesting to think about again, now that we're able to do this, there are these new kinds of technology like Alexa that we're putting out there in the world. What are different ways in which it could be used to help support various social groups? Okay, so let's switch gears now, and in lecture 17, we're going to look at a particular application of ubiquitous computing to again try and detect something among a social group that was difficult or impossible to do beforehand. We're going to start with the following question. Can we use ubiquitous computing technology to extract face-to-face information. So this is not texting using Twitter, face-to-face social interaction. Can we extract that from a social group? And can we learn about how people behave towards one another in that group? And more specifically, how they modulate their behavior based on who they're talking to or interacting with. Okay, so this is some work from about 10 years ago. The reading for today is this actual research paper. Like most of the reading that I've assigned, which are the actual primary sources, you can just read the abstract and the introduction. If you're interested, you can carry on and read the remainder of the paper. We're going to summarize, first of all, the methods section. What did they go about doing? They managed to convince 24 graduate students at the University of Washington to carry around sensors for a 6-month period. You can see 2 of the grad students here wearing them. There's sort of a small backpack on their back with a diagonal strap here, and there is a collection of sensors in this little device which is near their mouth and also near their ear. So this is important. They could have done this, they could have tried to do this on a cell phone, but again, physical context, most people have their cell phone in their pocket, and it's not going to be able to pick up normal speech as they're having a conversation. Okay. The sensors are going to record during the 6-month period. It's going to record the volume of their speech, these 24 grad students, and how they speak, but it's going to throw away what they say, right? So this is a pretty intrusive experiment. And remember, in HCI here, we need to think very carefully about our stakeholders. These 24 grad students have agreed to be participants in this research study. But what happens if there's a third person standing nearby that's also chatting with them and knows nothing about this study, right? They did not agree to anything. So we want to make sure that we're not actually recording any actual words, any actual speech, just how things are said, not what is said. Okay. From this raw speech data that is picked up by these microphones in these devices here, can we actually learn a social network? Who among these 24 graduate students are friends? If the only thing you have is this raw speech data, or sorry, volume and how they speak, it's actually not an easy thing to do. Of course, we could just give them a survey and they could tell us, but we want to see if we can infer it directly from ubiquitous technology, the sensors that they're carrying around. Okay. Then, assuming that we can learn this social network, is there a relationship between the way they speak and where they are in this social network? That is an extremely difficult thing to do if you're just a social anthropologist watching a bunch of humans interact socially. Very, very tricky to get at, right? Intuitively, you would think, yes, we probably modulate our behavior based on who we're talking to, but how? And to whom do we need to speak for that behavior to change? Tricky, okay. Okay, so obviously this is very intrusive. So these 24 subjects, although they were wearing it for a 6-month period, they were only wearing this backpack during working hours. They only wore it for 1 week per month out of these 6 months, and they only wore it for 6 months. Okay, they're wearing this device here, this MSB, and again, this was sort of state-of-the-art technology 10 years ago. Inside this device, there was a microphone, a triaxial accelerometer, which means that it can measure roll, pitch, and yaw, the 3 ways in which the thing is rotating, infrared visible light, a digital compass, temperature, barometric pressure, and humidity. They threw all of that away and just used the microphone data. The microphone data passed information to a PDA, which was in this backpack on their back. And at the point of capture, when they're capturing the data, they immediately scrubbed out the words. And this was, again, important because you could imagine capturing not only how they say things, but what they said, capturing it, and then offloading it to a device and then scrubbing it sort of downstream. But in order to really try and protect everybody's privacy, they were scrubbing out all of this privacy information upstream at the moment of capture. Okay. And then they had an SD card that was storing speech statistics. So volume, rate of speech, and pitch, which we'll see in a moment. Okay. Here's some of the raw data. Let's have a look at this data for a moment. Again, the captions are a little small here. Each of the 5 panels here corresponds to one of the 5 working weeks: Monday, Tuesday, Wednesday, Thursday, and Friday. The horizontal axis is from 9 in the morning until 8 p.m. And the vertical axis in each of these panels is person seconds speaking, or PSS. This is the total number of minutes that was recorded by these devices of someone speaking. We don't know who is speaking, but just there was speech being heard at that point. Okay. So, for example, if there were 2 people that were talking at the same time, if 2 of the grad students were talking at the same time during that period, there would be, for 2 seconds, we sum it all up. If it was 1 person talking for 4 seconds, comes to the same number. So we're just aggregating all of this information. Okay. Who other than the graduate students might be recorded by this microphone? Professors, right? So again, we're thinking about now the physical context or the social context, cultural context. Where are these grad students between 9 a.m. and 8 p.m.? If you were all wearing these devices, you'd be recording my voice, and you'd have a PSS of 75 at the end of this lecture. Who else might these microphones hear?
There could be double data, so you're talking to someone else with a microphone, and each person gets recorded twice.
Exactly. So if 2 of the grad students are in conversation, my microphone is picking up my voice, and your microphone is also picking up my voice, so we have a doubling. Who else? I guess if you're listening to YouTube during this period and someone's talking in the video, might pick that up as well, right? So not a person who's physically present. Okay, so we're looking at raw data here. We haven't done any analysis or manipulation of the data yet, but you can already start to infer something about the behavior of this group. What is it? Oh, did you have a question? Yep. It would pick up music, but as long as there wasn't any lyrics in it, then it would ignore that. So the microphone was looking for voice, someone speaking. So actually, yeah, lyrics, songs where someone's singing would be tricky. So 10 years ago, I don't know if their machine learning algorithms were sophisticated enough to pick up a voice in a song. My guess would be that that would be counted as other. What can you tell me about this group of graduate students?
They met on Tuesdays and Thursdays from around like 10:30 to 12.
Yep, looks like, yep.
Yeah, and then on like Monday, Wednesday, Friday, the time is a little bit shifted to around like 1 to 3.
Yeah, Monday, Wednesday, Friday, it's a little harder to tell, but there are clearly big blocks Tuesday and Thursday morning. What do you think those blocks correspond to? A class that they all shared, right? It was probably a class in which most, if not all, of the graduate students were present. Now, whether it was a seminar where they were all speaking or a lecture where the professor was talking, hard to say, right? But even with this raw data, you can start to infer something about the behavior of this group. Okay, so let's go now from the raw speech data and try and do the social network inference part. Let's assume at a particular point in time we had 3 graduate students sitting in a classroom, and the 3 of them were talking amongst themselves. While they're speaking, another conversation between grad student 4 and 5 starts up in the hallway just outside the classroom, and that second conversation starts before the first conversation ends. And assume that these 2 groups are far enough apart, maybe the doors of the classroom are closed, that the microphones 1, 2, and 3 are only picking up voices 1, 2, and 3, and microphones 4 and 5 are only picking up voices 4 and 5. Okay. Here's my little cartoon on the right of what the microphones might actually pick up. So we have speaker 1, 2, and 3, and we can see that for a certain time period, the volume of speech is either medium level or high. For microphones 4 and 5, there is also a period during which volume is either medium or high, and the rest of the time, in this time span, the microphone is saying there's no conversation or there are no voices nearby that I can detect. How do we go from that to inferring that 1, 2, and 3 are speaking amongst themselves and 4 and 5 are speaking amongst themselves?
So 4 and 5 overlap with 3 and 2. And one is like adjacent. There's no gap between 1, 2, and 3, and 4 and 5.
Okay?
But if you were to say there's like 1, 4, and 5, there's a gap between 1 and 4. So 1, 2, and 3, and then 4 and 5 being grouped is the only way where they're all directly next to each other without overlap.
Okay, so there's this period during which they overlap, right? 1, 2, and 3. That volume is either medium or high. But that's not sufficient to infer that they're in conversation amongst themselves. Because if you were all wearing a device, we would infer that you are all in conversation amongst yourselves for these 75 minutes, right? But during these 75 minutes, none of you are talking to each other, so I and no one else can say anything about who is friends with whom among this group. So that's good to start with this, but we need to do something a little bit more specific.
4 and 5, like 4's high volume drops off at the same, like at around the same time as 5 starts up, so you know that they're like responding to each other. Whereas 1, 2, and 3's drop off and pick up, match each other.
Exactly. There's a relationship between high and medium volume among these spans. And in order to detect that, the investigators used mutual information. This is sort of a fancy form of correlation. What mutual information tells you, or when mutual information is high, if I record a particular measurement here, whatever the value of that measurement is, it allows me to predict some other measurement somewhere else. There's mutual information. When I capture information here, that gives me information about something else that is happening somewhere else. Okay, so how are we going to apply mutual information? Well, imagine we march from left to right along these graphs. So we're marching forward in time. And we notice that there's a particular period of high volume. So we're going to focus on this particular point in time here. And the volume is very high here in saying that I hear speech. So we can be confident that microphone 2 is picking up the fact that speaker 2 is talking. Remember physical context. The device is very close to the speaker's mouth, which makes it relatively easy to say when the volume is high enough, even if they're listening to YouTube at a very high volume, they can tell it's the person who's wearing the microphone who's speaking. So during this period, during which speaker 2 is speaking, I've got some information now. I know speaker 2 is speaking, and I look at the other 23 microphones. Remember, there are 24 grad students wearing these microphones, and I try and predict what the volume is at those other 23 microphones. And it turns out that for microphones 1 and 3, they're always at medium volume during this time period whenever microphone 2 is high. So they must be near enough. If the volume is medium, they're near enough to be hearing what speaker 2 is saying. So there's high mutual information there. So during this short period of time, I can conclude at least that speaker 2 is talking, and speaker 1 and speaker 3 are probably listening. Maybe not. Maybe they're just nearby and have their headphones in, but I can be relatively confident they're close to one another. And I can do the same thing with speaker 1. When they're high, these two are medium, and when speaker 3 is high, there is high mutual information here. Whenever this is high during this period, I can predict confidently that these are medium. So there's high mutual information among these 3 microphones during this period. Whenever one of them is high, the other 2 is medium. I can confidently predict that. So I'm going to conclude if there's enough of that mutual information that 1, 2, and 3 are engaged in a conversation. During that period, at least one of them said something, and the other 2, I can't really conclude that they were listening, but at least their microphone was capturing the voice, and then they also said something, and the other people may or may not have been listening, but it was captured, right? We can't measure the conversation directly, but there's enough sort of corroborating evidence here that they're engaged in a conversation. Okay. Now, it turns out that when speaker 4 is high during this period, the microphone of speaker 3 is also medium, which seems promising. But mutual information is actually low in this case. If I take the period of time during which microphone 4 is registering high volume, there's low mutual information because I can't predict the volume of the third microphone in this case. While speaker 4 is speaking, sometimes speaker 3's volume is low, medium, or high. So there's low information, which is evidence against the fact that speaker 3 and speaker 4 are engaged in a conversation during that time period. So far, so good? Okay, so again, this is just a cartoon, but you can imagine doing this for this entire 6-month period and capturing moments in time in which subsets of the grad students are in conversation. We have no idea where they're in conversation. There may be multiple conversations going on among subgroups at any given time, but given the information that we're using here, we can infer conversations as they occur. Okay. So in this cartoon case here, we infer S1, S2, and S3 are in conversation, and S4 and S5. So we're going to start to take our raw volume data and transform it into a literal social network where nodes in the network correspond to the graduate students and edges connecting nodes together represent those individuals who are engaged in a conversation at that time. Okay. And remember, we're doing this for snapshots of time. So among, I can't remember, I think 5 or 10 minute periods during this entire 6-month period, they were creating these social network snapshots. In every snapshot, there were always 24 nodes, because there's always 24 graduate students. And then there may be 0, 1, 2, or more edges, which capture the fact that a subset were in conversation during that time. We're going to take all of those snapshots, there were thousands of them, superimpose them on top of one another, and just count the number of edges among those frames. And in this cartoon example here, there's one edge here, but not here, so we have a count of 1. S1 and S3 were in conversation during sometime on Monday, and then S1 and S3 were again engaged in conversation on Tuesday, so we have a count of 2. So at the end of this processing period, we have a single graph that has 24 nodes, and we have weighted edges, where the weight of an edge represents the number of conversations that we have inferred among that pair of individuals over that 6-month period. That's the social network that we have at the end. Okay, so we've gone from ubiquitous technology to a social network. Great that we can do that, but so what? What can we do with this information? Now we can get to some of the interesting things, which we can say, without the grad students telling us who among their group are friends and who aren't, we can start to ask questions like, how do they speak, or how do they change the way they speak, depending on where they are in this social network? Remember that we don't know exactly what they said, only how they said it. And it turns out that they captured 4 features of speech. Remember all the way back to when we were talking about the KNN algorithm, and there were 4 features of the flowers, the length and width of the petals. Same idea here. We've got speech data now. We're going to boil all that speech data down into different features. So at a given point in time when we heard someone speaking, we can tell the rate at which they were speaking. Were they speaking quickly, or were they speaking slowly? Pitch, were they speaking with a high voice or a low voice? Turn length, how long was their microphone recording high volume before their microphone recorded medium volume? So they've handed over the floor to someone else in the conversation and that person has started speaking. Turn frequency, if there were 2 or more people engaged in conversation, how quickly or how short were those time periods in which the microphone was registering high volume? What was the rate or frequency of turn taking in the conversation? And remember that we have these 4 features over time. So in any given conversation, we can ask what those 4 feature values were. We can derive that from the raw data coming off the microphone. So far, so good? Okay. Okay, so now let's start to test some hypotheses about social behavior in groups of humans that were difficult or impossible to pose and answer before we deploy this technology. First hypothesis we're going to look at is, do people change their normal way of speaking more when they speak to strangers than with good friends? Right? This is kind of an odd one to think about. What does your normal voice or non-normal voice mean? So let's try and quantify this. We're going to compute 3 values to begin with. The first one is bi/j. So bi/j is going to be the mean of person i's speech feature b. We have 4 possible speech features, so we can plug in any one of these 4 for b. We can ask, what is the value of that feature for person I when speaking with everyone else they spoke to among those 23 other graduate students during that 6-month period? So I am person I, I'm friends with Jack here. Jack might be J. I can ask, how did I speak when I spoke to everyone else that I spoke to during that 6-month period except for Jack, except for J? Then I can also compute I arrow J, or I'll just say Bij for now, the mean of I speech feature B when speaking with J. So at any point in time, we're going to pick within that group of 24 graduate students, 2 grad students, I and J, and ask, how did they speak? What was the tone of their voice or the feature of their speech when I spoke to J? And what was I's way of speaking when I spoke to everyone else except J? Okay. We're then also going to compute S sub I, which is the standard deviation of I's speech feature B, regardless of the interlocutor. Interlocutor is the other person that I was speaking to. Some people speak very differently when they speak to different people, which would mean that person I would have a high S sub I. Other people, behaviorally, just don't change their speech very much, depending on who they're speaking to. They have a relatively low S sub I. So we're going to compute this value D, and we're going to divide by S sub I. So we're basically normalizing by S sub I, or we're trying to remove this other piece of behavioral data, which is some people change their voice more or less, depending on who they're talking to. We're removing that piece for now. Okay. We're going to normalize this value D sub ij, which is the amount that person I changes their speech when they talk to person J. So I speak to a whole bunch of different people, and I also speak from time to time to Jack, who's going to be person J. D sub I is going to tell me how much I change my way of speaking when I speak to Jack, compared to my average way of talking to everyone else that I talked to during that 6-month period. So far, so good? Okay. So we're taking the absolute value of bi/j minus bi arrow j. What would happen if the numerator, what would it mean if the numerator here is large? What does that tell you about individual I and individual j? So we're subtracting 2 values and taking the absolute. So if we want to think about a high value, that means that those 2 elements in the numerator have to be very different, which means what?
That you do talk to them differently.
I talks to J very differently from the way in which I talks to everybody else, right? That's all Dij for the moment is going to tell us. So far, so good? Okay. Finally, we're going to compute Cij, which is the fraction of time that I speaks to J. Okay, so we have in hand now C and D, and we've computed it for just 2 people, I and J, and only for cases in which I is talking at J and also talking at other individuals. We're going to compute C and D now for every pair of individuals among that group of 24. And it's too early in the morning for me to do that computation, but there's quite a few of them. right? So we've got a whole bunch of Ds and a whole bunch of Cs, and we can then ask, is there a correlation between C and D? And it turns out that there is. There's a negative correlation, which means lower C, higher D, and higher C, lower D. Okay. Remember that we're computing these values for B, which is one of the 4 speech features that we have here. So I'm writing out, or I've reported for you here, the 4 R values, which are these 4 correlation values for each of these 4 features. So we collected all of these C's and D's for rate, looked to see whether there is a correlation, and there was a negative or anti-correlation. Then we computed all the C's and D's for pitch, and there's still a negative correlation, but it's less. Did the same thing for turn length and turn frequency. So for almost all of these 4 speech features, higher C meant lower D. Or sorry, lower C meant higher D. What does that mean? Let's just focus on this one. Among all the grad students, whenever C was low, D was high. What does that mean?
Means when you're talking with someone you don't talk to very often, you speak very differently.
That's it, right? Which again, maybe in retrospect makes sense, but now we quantitatively have that in hand, and we can ask, how do they speak differently? Well, they change their rate, they also change their pitch, they also change their turn length, and the last one, their turn frequency may or may not be significant. So I probably wouldn't trust that 4th one, but at least for 3 of these speech features, yes. Question? So R is the amount of correlation or anti-correlation. So R is a value that can range between +1 and -1. A value of +1 would mean they're perfectly correlated. Whenever one goes up, the other one goes up. When one goes down, the other one goes down. An R of -1 means they're perfectly anti-correlated. Whenever one goes up, the other one always goes down. And when one goes down, the other one always goes up. An R that's near 0 means they're independent. There's no real correlation between them. So the negative value here tells us there's an anti-correlation. Most of the time, when C goes up, D goes down, and vice versa. But it's not -1, it's -0.2. So it's not that strong, which you would expect. We're dealing with human beings. Human beings are very complex. We're also using some technology which isn't perfect. So it's kind of washed out. The p-value over here tells us the probability that our hypothesis is wrong. Okay? So a p that's close to 1 would mean there's a 100% chance that that hypothesis is wrong. People don't change their way of talking when they're talking to people they don't talk to very often. The lower a p-value is, the lower the probability that our hypothesis is wrong. You can thank the statisticians for all these double negatives, right? It'd be better to have a probability that tells us the chance that our hypothesis is right. For certain reasons, we do it the other way around, right? So we can say it looks like there's very low probability that our hypothesis is wrong, right? Which is kind of a modest way of saying, I think we're right. Make sense? Okay. If you're following so far, you might then want to answer the question, well, did they speed up their way of speaking when they spoke to strangers, or did they slow down their way of speaking when they speak to strangers? This says nothing about that, just that they changed their rate of speaking. You can make arguments for either case. You could imagine diving back into the data and computing some other values. You could probably actually get at that hypothesis as well. Okay. Okay, let's look at the next hypothesis. So if you look at the top of the slide for a moment, so we're going to look again at whether people change their normal way of speaking. Now we're going to ask, do they change their way of speaking when they speak to well-connected people? This one's kind of interesting. First of all, what do we mean by well-connected people? And if people do actually change their normal way of speaking when they speak to well-connected people, that means they know who's well-connected among the group of 24 graduate students. Okay, So same thing we did before. We're going to compute bi/j and bi arrow j. We're also going to normalize by s sub I. So we're going to come back to dij. And remember, dij just says how much I changes their way of speaking when they speak to j. Now we're going to change our c. We're not going to have cij anymore, just cj. So I is speaking to j, and j is going to be, cj now is going to be a measure of the centrality of j in the social network. What is centrality? It is simply how many other people and how many conversations j had with everybody else. As you can imagine, this is a proxy for popularity or social hierarchy. We're not going to use those words because they're very loaded. We're going to just say, we're looking at someone who has high centrality tends to engage in lots of conversations with lots of the other 23 graduate students. So someone who speaks rarely, and when they do, they only speak to one or a few other graduate students, would have low centrality. So far, so good? Okay, so now, again, we have a collection of Ds and Cs for all the Is and Js among the 24 graduate students. And we can then ask for each of our B speech features, is there a correlation between them? And in this case, there's a positive correlation. You'll notice that all the values here are now positive, again, with the exception of the fourth one there, which is not significant. Can't tell anything about turn frequency. But for the other three, whenever C is low, D is low, and whenever C is high, D is high. Let's talk about low C and low D. What does that mean about the behavior of the group? So low C is low centrality.
So when you're talking to someone who talks to a lot of other people, there's a larger difference in how you talk relative to someone who doesn't.
Absolutely. So remember that it's C sub j here. So j is the interlocutor. It's the person who is being spoken to. And I is the person who's doing the speaking.
Thinking back on what I just said,
Yep.
isn't that kind of a paradox? Because if you talk very differently to someone who talks to a lot of people,
Yep.
the person who talks to a lot of people will also probably talk to you a lot because they're talking to a lot of people. Therefore, how can you be talking very differently?
If there's a lot coming back the other way.
Right.
So there's another hypothesis. If you have high centrality, you're engaged in a lot of conversations, is it as bidirectional as in other conversations? I don't know, maybe, and in which case there might be a little bit of circular reasoning in here. Hard to say. Let's assume that that's not the case for the moment. Low CI, so if you're talking to someone who has low centrality, you as speaker I do not change your speech very much compared to how you normally speak. But when you are speaking to someone that has high centrality, you change your way of speaking much more than the way that you normally speak. At least in terms of the rate at which you speak, the pitch of your voice, and turn length.
What would be the basis for somebody's normal speech?
The basis is BI/J, right? So I'm I and I'm speaking to Jack. You want to know what my normal way of speaking is? It's the way I speak to everybody else. That's right. Exactly. Are you surprised by this finding? Some people, yes. Some people, maybe not so much.
Not really, I guess. So it's sort of going taking the opposite side of what that person said. If you think about the low centrality person's I, you could think that maybe they're shy or just an introvert or they just don't talk to many people. When they do talk to someone, maybe it's their friend or someone that they would talk to normally.
Right.
They might be slightly intimidated or someone by a exuberant extrovert or something.
Possibly, right?
So they might behave differently.
Absolutely. So they may behave differently. There's clearly probably introverts and extroverts in this mix. So we could then ask hypotheses about why we obtained this particular finding, and maybe the raw data that we have is enough. We could go back and condition the data in another way, and we could ask something about C sub I. What about if the speaker has low centrality or high centrality? What sorts of relationships could we find there? Okay, so think about the results that we have here. Imagine now going back 10 years before this experiment, so going back 20 years, and trying to test these hypotheses without this technology, right? Nearly impossible. As we know from social network apps, there's lots of interesting social behavior that was hard to see before apps existed, but there are also a lot of subtle social interactions that go on when you're speaking face-to-face with someone that have never been measured. There have been hypotheses about those behaviors, but it's been impossible to test them before. These are just two hypotheses. You can start to imagine many, many more. Makes things interesting about what can we learn about human behavior as humans are walking around an environment in which, for better or for worse, we're being recorded in lots of different ways. Interesting to think about. Okay. So that's lecture 17. We're making good time here, so we're going to jump into the future a little bit. I haven't had time to put up lecture 18 yet on activity tagging. We'll start in on the first few slides of that this morning, and then we'll come back to it next Tuesday. Okay, so we're now going to look at a second project, a research project. And again, this one has to do with something that was difficult or impossible to do before, which sits within a larger domain, which is now known as mobile health monitoring. We'd like to be able to measure in near real time, as best we can, our physical and mental our physical and mental well-being, or at least some of us would like to do so. Tricky, right? Again, we could survey all sorts of things, but we can't measure well-being directly. The only thing we can really measure are the behavioral correlates of well-being, right? And again, this is already controversial, but generally most people would agree there are aspects of your sleep behavior, physical activity, intellectual stimulation, social interaction, diet, stress, and so on. There's something about those behaviors that positively or negatively impact your physical and mental well-being. So we're going to try, using ubiquitous technology, to not measure well-being directly, but to measure some of these correlates, and then use these correlates to predict physical and mental well-being. Again, this is going to be a little bit tricky because what do we actually mean by well-being here? Okay. Diet has been around for a long time, long before ubiquitous technology or technology at all. You might manually record what you eat. Now you can do it in an online journal. There are, I would imagine, hundreds of these websites now where you can actually do this. I don't know if you've ever tried, but it is a real pain in the butt to do this. What are some better ways we might be able to record diet than having to type in how many peas you ate last night?
Just looking at what you purchased at the supermarket.
Absolutely, right? So that's a possibility. But again, that's tricky because maybe you're not just buying for yourself. And if you buy 20 pounds of hamburger, how quickly did you eat it all? Who knows?
You can do it with photographs.
Photographs? Yeah, I think there's some websites where you do that now. You take a picture of your food and upload it, and it tries to analyze that. Again, that has its pros and cons.
This is a bit tangent to diet, but I think that there's like an app now for diabetics where it will monitor their sugar.
It monitors blood sugar? Yep. How?
They have like a patch on their arm and it's just next to their phone.
Exactly. So we're going to talk about wearable technologies in a few weeks' time. So if we're talking about diet, wearables might be a way to go. There's actually a sensor out there now that you could wear on the inside of your mouth that will detect sugar and protein and fat content in whatever you eat. I don't know about you, but that seems a little bit unacceptable to me from an HCI point of view, but maybe not. Okay. Diet's tricky. Some of these other ones are also tricky. So let's see if we can do this in as non-intrusive a way as possible. So we're going to try and create monitoring technology that is acceptable. Someone would be voluntarily willing to use it. And we're going to try and measure these things continuously and automatically. So rather than asking someone to type in what they ate for dinner last night, again, we want this technology to fade into the background where they can just go ahead and eat normally, and we will try and record it as best we can and as continuously as possible. Assuming we can measure these behavioral correlates of well-being, we're going to create some machine learning. We're going to create a model that takes as input measurements and produces as output a prediction about well-being. Is whatever it is that you're doing positively or negatively impacting your well-being? Some of these aspects will be easier than others, as you can imagine. Okay. Then, in addition, we're going to create a nice visual interface where we'll show the user the raw measurements continuously and let them also draw their own conclusions. So perhaps, depending on who you are, you would rather have your app tell you that what you're doing is good for you or bad for you, or maybe you'd rather just see the data itself and make your own decisions about whether and how you want to modulate your behavior.
So, like, for example, like, I'm trying to wrap my head around mental well-being.
Okay.
So when you eat a hamburger, you'll get like a spike of happiness, but is that well-being because there's a natural downtrend after that because of
Absolutely,
what
right?
you're eating? So I feel like time is a massive kind of variable.
Absolutely. So again, this is a massive undertaking. This is a 30, 40-year project for society as a whole. We're going to basically look at the low-hanging fruit, some of the easier things that are able to detect, which clearly have an impact on your well-being. Most of you, if I were to ask you, could probably tell me how many hours of sleep you got last night. Most of you could probably tell me whether you got the right amount of sleep or not, more or less, right? Not exact, but more or less. How many of you could tell me how many hours of sleep you got the night before? The night before that? The night before that? Did you get, on average, more sleep this week than you got the week before? Maybe since it's midterms, you could tell me you probably got less than the week before. What about this month compared to last month, right? So again, you could probably do this more or less if you had some of the data available to you, which you have, but that data fades pretty quickly, right?
Our natural cycles like take it into account. You know, like I'm awake right now, and at like 11 p.m. I'm gonna be tired because I haven't slept all day.
Yeah.
I'm gonna be hungry before I eat, and then after I eat, I'm not gonna be hungry.
Which comes back to this time period. So in terms of the short term, we're probably never going to do very well, right? You feel great when you had a burger. You don't feel tired now. But if we could see how many burgers you ate over the last 2 weeks, or how many hours of sleep you got over the last 2 weeks, then maybe we could make a prediction about your well-being over the next coming couple of weeks.
How's it going to account for the stress caused by the act of tracking and monitoring your own well-being?
Good question, right? Exactly. We won't have to because you're going to forget pretty soon that we're actually recording it. In the short term, maybe it'll bother you, but if it's doing its job, it should fade into the background. This is all, again, assuming that you voluntarily want to do this. Okay. Which of these 1, 2, 3, 4, 5, 6 correlates are easier to measure than others? Not which ones are more predictive of well-being, which are easier to measure than others.
Sleep.
Sleep is an easy one.
Physical activity.
Physical activity, maybe, a little trickier. Why is physical activity a little trickier than sleep?
Because different people have different thresholds for like heart rate and other general indicators of physical activity.
True?
Stress.
Let's stick with physical activity for a moment. We're going to try and measure this continuously and automatically. Why is this tricky?
Back to me.
Yep.
Okay. Well, in terms of why I said it was easy to measure, like Fitbits now, they'll be able to tell you like if you're on the elliptical or if you're running or if you're doing crunches, so they know that there's certain motions associated with certain physical activities.
Absolutely. And this experiment that we're going to look at today, 2011, this was one of the precursors of Fitbit, right? So with technology now, it definitely is easier. I don't have a Fitbit. I have a smartphone. When I go on the treadmill, I don't have my cell phone with me. So if I'm not wearing a Fitbit, it might be difficult. I might manually type it in after the fact, but we're assuming we want to try and collect it continuously and unobtrusively as possible. And Fitbit is the best attempt so far to try and do that. What are some other correlates here that are easier or harder than others?
We just showed that with the microphone we can track social interaction.
Social interaction, right? So difficult but not impossible, getting easier.
Does social interaction include interaction with people online?
Ah, exactly, right? What do we mean by social interaction? We can measure maybe face-to-face conversation. Maybe we can also record online social activity using a different set of sensors and bring that data together. How many conversations were you in throughout the day? How many of them were in person and how many of them were online? You could probably start to get at that data.
Stress is easy to measure.
Stress is easy to measure. How so?
Body temperature and blood pressure.
So Fitbit or other wearables, you can get at physiological responses that correlate pretty well with stress. Okay. So again, keep in mind this experiment we're going to look at is 7 years old now, and it sort of shows the rate of progress in HCI. A lot of what you're going to see here is already outdated, but it's an interesting experiment to look at because it was the precursor for a lot of these devices that now attempt to try and measure continuously and unobtrusively correlates of physical and mental well-being. Here's the little fancy figure from their paper. So we're going to go round and round this cycle of monitoring behavior and then using raw data to try and model well-being. So we're going to take raw number of hours of sleep, put that through a model, and the model is going to say you haven't gotten enough sleep over the last 2 weeks, or you're getting enough sleep over the last 2 weeks, and then provide that information to the user in some way. Does this user want to see the raw number of hours they slept? Would they rather an app that just says you're doing well or poorly in terms of sleep? Depends on the user. What exactly do they want to see? Here's a snapshot of the app that was created and reported on in this paper. So in the top left panel here, we're seeing actual raw data, and we're seeing the beginnings of activity tagging. So green here is does the microphone or the smartphone register noise, something else, a voice, complete silence. And down here, the accelerometer in the phone is starting to infer something about activity. So the app thinks that you were stationary at a certain point of time, walking, running, and what have you. Which activities are easier to measure or predict than others? Stationary is pretty easy.
Things with repetitive motion would be easy to detect.
Absolutely. So walking and cycling, that's relatively easy.
Sound, like whether it's sound or not.
Okay, yeah, sound is relatively easy, as we saw in the previous lecture.
Sleep.
Sleep, okay. What else? Okay, let's carry on and look at some of the other data. So again, at the top here, we've got more or less raw data, and as we move down here, we've got more conditioned data. So in the middle panel here, for 3 different days, October 8th, 9th, and 10th, they were looking at the number of hours in which there was some sort of physical activity, walking, running, cycling, and so on. Social activity, what went into that box? Not quite clear yet. And then sleep. I feel bad for this particular person. They had 10 hours of sleep on one day and none the next day and none the day after that. Seems a little strange. Okay. Let's focus on sleep. Okay, so sleep seems like it would be an easy one, right? Okay, let's assume you have the following. We'll end with this example today. Let's say you've got the following sensors available on your phone. You have a binary indicator of whether the battery is being charged or not. You have clock, accelerometer, digital compass, GPS, microphone, and camera. How are you going to take that raw data and turn it into number of hours that someone slept per day?
So first of all, with the clock, you know that most people sleep at night.
Yep.
So if it's night, if the phone isn't moving, I plug my phone in when I sleep.
So do I.
That
Okay.
would be one thing. And then if it was really quiet.
Okay, so silence, night, batteries plugged in, and what am I missing?
GPS at home.
GPS at home. Okay, so we could take 4 of these elements and try and combine them to corroborate the fact that you're asleep, right? Any one of them might not be very reliable, but we can combine them. Is that good enough? Midterms are a good time to think about this, right? Is the only sleep you're getting at home at night? I know when I was an undergraduate, I nodded off in the library from time to time, right? Which maybe misses half an hour, or when I was really stressed, 2 hours. Right? Depends on the time of year for me, right? So good, but again, there are those edge cases that are going to be tricky to capture. Think about that. You have a quiz due tonight. Start in on Deliverable 9 at your leisure. Professor Bagwell will be guest lecturing on Thursday. I will see you all on next Tuesday. Thank you.